Greetings! This is the first 3 problems of suggested problem set 1.2 for my AP Physics class. So we're going to start with 2.10 here. A physics professor leaves her house and walks along the sidewalk toward campus. After 5 minutes it starts to rain and she returns home. Her distance is shown as a function of time in this graph here. So we want to go through this and look at these labeled points in Roman numerals 1 through 5. And decide which of these labeled points is her velocity 0, constant positive, constant negative, increasing, and decreasing in magnitude. So I'm going to go ahead and come over to this table, or come over to the side here, and I'm going to make a little bit of a table. So I'm going to say velocity equals 0 is one line. I'm going to say constant and positive is another line. Constant negative, another line. Increasing, and I'm going to say that's in magnitude, so speed is increasing, and then decreasing in magnitude. And so we're going to see what are the hallmarks to look for this. So let's start with velocity equal to 0. So this is my position over time graph, so I know that velocity as a function of time is the slope of my position graph. So if I'm looking at the slope for these, the only time when velocity might possibly be 0 is right here at Roman numeral 4, when the slope of the tangent line, here sketched in orange, is approximately 0, it appears. So I believe only Roman numeral 4, actually, let's try a different color, only Roman numeral 4 is a situation where we have 0 velocity. So looking at positive constant. So the velocity would be positive and constant, and we're going to be looking for a section where the slope is positive and constant. So the only situations where the slope is positive are at 1, 2, and 3, and it appears that at 2 we have a slight curvature to our graph. The same is also true at 3. Now at 1, it does appear to be linear. So I would venture a guess to say that the slope, and therefore the velocity, is positive and constant at 1. Where is it negative and constant? Well, the only position where it's negative slope at all, and therefore negative velocity, is at 0.5. And it does appear to be linear, so our slope and velocity must be negative constant. I will not draw my capital V, I will instead do Roman numeral 5. So then looking at increasing in magnitude. So this is a little bit more interesting to think of. So if you are familiar with calculus, the second derivative of a graph is also known as curvature or concavity. So I want to look at my graph and see where, if I want an increasing magnitude, my graph is concave up. So concave up, which looks like this, like an upward facing U, implies that acceleration is positive for that section. So if I look at my graph, I can see that near Roman numeral 2, I have concave up, and therefore I can tell that my acceleration should be positive. Similarly, if I want to look at decreasing in magnitude for my velocity, I'm looking for a section where my graph is concave down. And so again, that would look something like this, where I have a downward facing U. This tells me that my acceleration is negative for that region, and therefore my velocity should be decreasing in magnitude. So in this case, my decreasing in magnitude section would be right here at Roman numeral 3, where I have concave down as my graph. So again, we're looking at the slope of this graph, and we are also looking at the concavity of this graph in order to tell how velocity is changing. Moving on. So question 2.17 gives us a velocity function for a car. So I'm going to start with my velocity function. I'm going to go ahead and substitute in these constants that were given to me. So I have 3.00 meters per second plus 0.100 meters per second cubed times the square of t. So A says calculate the average acceleration for the time interval from t equals 0 to t equals 5 seconds. So the key word here is average acceleration. So I want to recall that acceleration average, and I should say A average in the x direction, is equal to the change in velocity over the change in time. So my change in velocity I can think of as Vx of 5 seconds in this case minus Vx of 0 over my 5 seconds minus my 0 seconds. So I'm going to go ahead and substitute in here and find values for my velocities at these two times. So at 5 seconds, I'm going to have 3 plus 0.1 times the square of 5 minus 3 plus 0.1 times 0, all over, I think we can all agree that 5 minus 0 is 5. So doing some math here, and hopefully you have a calculator handy, we should see that 3 plus 0.1 times the square of 0.5, or the square of 5 rather, subtracting 3 divided by 5 gives us an average acceleration of 0.5 meters per second squared. And I can tell it's meters per second squared, meters per second squared, because my velocity will work out to be meters per second over seconds. Part B asks us to find the instantaneous acceleration for t equals 0 and t equals 5. So part B wants instantaneous acceleration. So this is equal to the first derivative of my velocity as a function of time. So my velocity function is 3, I will go ahead and take the derivative here. My velocity function being 3 meters per second plus 0.1 times t squared. The time derivative of 3 meters per second is 0, and the time derivative of my second term is going to be 2 times 0.1, which is 0.2 meters per second cubed, multiplied by now t to the first power. So my acceleration at 0 seconds will just be 0.2 times 0, which is 0 meters per second squared. And my acceleration at 5 seconds will be 0.2 times 5 seconds, which is 1, and if you want to go with significant figures here, 1.00 meters per second squared. So here are my two instantaneous accelerations, again found with the derivative of velocity with respect to time. The final question asks you to draw velocity time graphs and acceleration time graphs for the car's motion between 0 and 5 seconds. So I'm going to go ahead and sketch up some axes here. So I have one set of axes for velocity in the x direction as a function of time, and another set of axes approximately the same size for acceleration over time. So we're just sketching here, but my velocity is a quadratic or a parabolic function, and so I want to have, for the first 5 seconds, something that looks parabolic. And since it's asking you to sketch, and we have a little bit more information than just the shape, it is probably prudent to insert some values where possible. So if I go back to part A, I did find the velocity at 5 seconds. I didn't write the intermediate value, which would be 2.5 plus 3, or 5.5 seconds, or meters per second. But it is not too difficult to find that. And so here is my sketch of velocity over time. Again, it's a parabolic function. For my acceleration, I look at this function that I have. So it is 0.2 times t, and so that is a linear function with a slope of 0.2. So I'm going to go ahead and just sketch a linear function. And then at the 5 second mark, I should have a value of about 1 meter per second squared. So here are my two sketches for graphs. Again, the important parts are we know an endpoint. We also know the approximate shape of the graph. Moving on to question 2.30. talking about a cat walking in a straight line, which we can see in this figure 2.30 here. Measurements are taken, and we want to, for part A, find the cat's velocity at 4 seconds and 7 seconds. So this first part is simply reading a graph. So at 4 seconds, I'm going to go to my 4-second mark, read up to here, and then approximately say that this is where my graph meets. And I will say that my velocity at 4 seconds is approximately, I will say 2.5, and this is positive, this is a positive value, 2.5 centimeters per second. Make sure you look at your units. Similarly, the velocity at 7 seconds appears to be somewhere down here. Well, this is where I finally realized that something is a little interesting, and just finding these points is rather difficult. So instead of actually just reading the graph, a better idea might be to take your 2 points here and find an equation for this line. So my slope of this line, I'm going to take 2 points. I'm going to take this point, my x-intercept or my time intercept, and my vertical intercept, and I'm going to find the slope. So this point right here is 6, 0. This point right here is 0, 8. And so to calculate my slope, I'm going to have y2 minus y1, so 0 minus 8, over x2 minus x1, 6 minus 0. So this is negative 4/3. So then I'm going to go ahead and find an equation using point slope. So I'll do y minus, we'll say 0, equals negative 4/3 times x minus 6. So if I put this into slope-intercept form, which is typically more useful for us, we have negative 4/3 x minus 8. Or I'm sorry, plus 8. So here's my equation. So I can actually go back and double check my work for what I wrote before. So instead of just reading off my graph, now that I have an equation, which I should rewrite into Vx equals negative 4/3 t plus 8, I can write that the velocity at 4 seconds will be negative 16/3 plus 8, or, with some calculator magic, 2.666 repeating meters per second, or centimeters per second. And my velocity at 7 seconds will be, again with some calculator magic, or you can leave it in a terrible mixed fashion, negative 28/3 plus 8. We get negative 1.3 repeating centimeters per second. And so I can actually look at my graph and see if these are realistic numbers. So given my uncertainty here, this seems realistic to be about 2.6, and somewhere down here at 7 seconds, I assume that that would be approximately negative 1.3. So B asks for the cat's acceleration at 3 seconds and 6 seconds. Well, I just went to the trouble of finding an equation that has a slope for it. And I know that acceleration is the slope, or the first derivative, of my velocity function. So my acceleration at all points, so this is still part B, at all points should be negative 4/3 centimeters per second, or centimeters per second squared. So it doesn't matter where, because this is a linear function, I'm looking. My slope, and therefore my acceleration, should be the same. Now C asks us to find the distance that the cat moves for 4.5 seconds. So this is a little more interesting. So I'm actually going to want to look at my graph again, and I'm going to want to find the slope, I'm sorry, not the slope, the area for this section of my graph. So for the first 4.5 seconds, I can go through and find this area. So I'm going to go ahead and find this point. So I want to find velocity at 4.5 seconds. And so plugging that into my equation from part A, I have negative 4/3 times 4.5 plus 8, which is around 2 centimeters per second. And so I have two sections here. So this is right at 2, so I have a rectangular section and a triangular section. So my area here and therefore my displacement is going to be 2 centimeters per second times 4.5 seconds plus the triangular area, which is going to be 1/2, and the height of this is going to be 8 minus 2 centimeters per second, times, again, the base of 4.5 seconds. So, taking this to the calculator, I'm going to have 9 plus 3 times 4.5, which is a displacement of 22.5 centimeters, because one of my seconds will cancel out. So it also asks for the displacement from 0 to 7.5 seconds. I will leave this for another time. If you would like to ask, please do so in class. Then finally, D says, assuming the cat started at the origin, sketch graphs of the cat's acceleration and position functions. So part D wants an acceleration graph and a position graph. So here's my acceleration graph. My position graph will follow. And so my acceleration graph is simply going to be, and I should do this rather differently. I should have a negative side to my graph, because my acceleration is a constant -4/3. And that's, of course, centimeters per second squared. Now my position graph, and this is just going to be a sketch, is going to have a negative curvature because of my negative acceleration, and it is going to have a positive slope to begin with, and it is going to eventually be a negative slope. So I'm going to draw something that looks approximately like this. So I have negative curvature, it's curved downward. It has a positive slope to begin with, which decreases to 0 at some point. And if I want to have a particularly important critical point here, that occurs at the 6-second mark, where my slope goes to 0.